So today I'll finish talking about wheels and go on to talk about bumper cars. And before I do that, I'll remind you there's no class Wednesday. And so the next class will be Friday. And since I have office hours normally on Wednesday mornings, I'm going to move them to Friday morning. So I'll be in my office downstairs Friday 9 to 11 in place of Wednesday. I'll have my usual office hours today at 3 to 5 in Alderman Cafe if you want to come talk about whatever, including the problem set that's due on Friday, not on Wednesday because of the UA. Any questions about class logistical stuff? All right. Where I essentially left off was talking about friction. Wheels, the purpose of wheels is to control friction, and not to totally eliminate it. If you totally eliminate it, you can't steer, you can't propel a vehicle. Friction's used very strategically by wheels to make vehicles do good things and not do bad things, or at least trying. And toward that end, I want to make sure it's clear to you how the two different types of friction, there are actually more than two, but two major classes of frictional forces, how they work. One of them involves relative motion, one of them doesn't. One of them involves wasting energy as thermal energy, and the other doesn't. And so I'll try to illustrate these and ask me questions, as usual, if it's not becoming clear. Static friction. First off, frictional forces are the other possible force between surfaces. I showed you that support forces are exerted perpendicular to surfaces. So this horizontal table can only exert upward support forces. That's what it does, okay, that's all it can do. The other possibility, perpendicular is this way, they're all the parallels that are possible. Actually, there's a whole variety pack of those directions that are parallel. Anything in between perpendicular and parallel is a combination of the two. It's partly perpendicular, partly parallel. So the point is that frictional forces act along surfaces, parallel to them. Support forces act perpendicular to them. Is that okay? The two kinds of frictional forces that show up between the table and, say, the bottom of my little wagon are static frictional forces and sliding frictional forces. Sliding frictional forces are also called dynamic frictional forces if you've encountered them before. Same idea, just different name. So static friction is between two surfaces that are trying to slide across each other but haven't started doing it. So they're gripping each other and there's no movement of one relative to the other. And that's going to be the case when I pull on, I think I can do it with this scale. So if I pull this wagon to the left, come on, there we go. If I pull it to the left, it doesn't start moving. Why not? I'm exerting a leftward force on it. It should accelerate to the left. But it's not because the table is pushing it to the right with a static frictional force. The frictional force between two surfaces that aren't moving across each other. And that frictional force is adjustable. It can go from 0. Right now I'm pulling 0 to the left, so it pulls 0 to the right. Now I'm pulling 4 to the left, it's pulling 4 to the right. And I think it gets all the way up to 20 before it starts up. No, I got to about 11. And then static friction gave up. I get to 10 maybe. So depends on where I am on the surface. It's very dependent on the nature of the surfaces, how rough they are, and how hard they're pushed together. So I've got that big block in there to push them hard. And they grip each other all the way to 10 newtons of force, 11, 12. Ooh, I'm getting a good stick this time. 13, 14, up, and then it gave up. And when you notice when it gave up, the force dropped. And that's typical of what happens when static friction gives up. So static friction is, I think of it as microscopically, it's the surfaces being not perfectly flat, sort of interdigitating in some manner and getting a grip on each other. And they fight the relative movement up to a point, and eventually, they give up, and those little fingers begin to bounce off each other and skittle along. And so what you could see in this, if you're watching carefully, was the grip is pretty strong until finally it lets go, and then you get a weaker residual force that continues as the surfaces actually do slide across each other. So the first part, I'll get rid of the scale just so I can do it easier with it by my hand. The first part, this is static friction, and it's adjustable, and it goes up to a certain limit, at which point it fails to hold the surfaces motionless relative to one another. What else about it? Oh, the frictional force is always in the x in the direction that tries to make the other surface move with this surface. So the table, being motionless, wants to make the wagon stay motionless. So its frictional force x on the wagon, trying to make sure the wagon doesn't move. So when I pull to the left, the frictional force of the table on the wagon is to the right. And if I moved around and pulled to the right, frictional force would pull left. It's pretty straightforward. Okay? Once static friction gives up, you get this force of sliding friction, which is different. It's a specific value. It depends on the surface, but it was about 10 newtons on this, between this wagon and that table. It's about 10 newtons, and not much I do will change that. It wants to be about 10 newtons. It does depend on how hard the surfaces are pressed against one another. It does depend on the surfaces themselves, but it's sort of one specific value. That's sliding friction. All right? Let's see whether. No. Okay, so apart from the two different forces, anything else interesting about them? Well, static friction does not waste energy, but sliding friction does. So to give you an illustration of that, right? I mean, the simplest is this. If I pull to the left on that wagon, I'm pulling to the left, but the wagon's not moving, so I'm doing no work on the wagon. The wagon is pushing the table to the left with a static friction force, but the table's not moving, so it's doing no work on the table. The table is, basically, you look at for all the forces that are involved, there's nothing moving, so there's no work done. No energy is moving around between any of us. On the other hand, I want to remember to ask my question the right way. All right. So what about sliding friction? Well, to make sliding friction the clearest thing going, and I want to go to, it doesn't matter which direction. I'll show you my question in a second. If I get this guy going, so that before the story starts, I'm going to get the wagon going to the right, and watch what happens. The wagon stopped. I gave it energy when I pushed it to the right and it moved to the right. I gave it energy, and it had that energy as kinetic energy, and then it stopped. So something bad happened here because it stopped, and we don't know where the energy went. Well, I mean, nothing obvious happened here. And the question I want to ask you is this one. So when the box in this wagon skids to a stop on a motionless table, what work is done on those two objects? So the box/wagon and the table. You okay with the question? Are questions on the question? All right. Of course, I forgot to start. I'm going to have to get this out of the way 1 second. I got to start the clicker program, which I forgot. Clicker, clicker, clicker. Oh, yes, start new session. Yay. I'm so happy. All right. Oh. There. Okay. You okay with the question now? After you watch me, and now it will ask me, do this? Yes, no. I don't want to see that ever again. Okay. See what you think. And you could talk among yourselves about it. Who's doing work on whom? Table, wagon, wagon on table, and so on. I forgot I get a preview. I can see what people are doing. All right, finish up at the 60-second point. All right. Well, it's between A and E. So everybody is okay with the idea that the table is doing negative work on the box. Because the table, in this case, the box was skidding to the right, and the table was pushing it to the left to stop it. So if it was moving to the right but being pushed to the left, the table was doing negative work on it. That's correct. So far, everybody okay with that? The question comes about is, was the box doing positive work on the table or not? What would the table have to do? The box was definitely pushing on the table. If that was your foot or something instead of the table, you'd feel it skidding along you. Is the box doing any significant work on the table, though? Why not? It's not moving. So the actual answer is A, which looks like a disaster for the conservation of energy. This is a case where the table did negative work on the box, pushing it to the left as it moved to the right and sucking the energy out of it. But the box did not do positive work on the table because the table didn't move. All right? It's a mystery, or briefly a mystery. Where did the energy go? And the energy got ground up into tiny little bits of energy in the table's top surface and the bottom of the wagon. The two of them skidded along each other, shook things up locally, in effect did microscopic bits of work on each other by pushing a little piece and having it move in that direction, then something broke or snapped back to its position. So the energy was all ground up, and it's now in the two surfaces as thermal energy. And that's what sliding friction does, is it creates, it always turns some amount of work into thermal energy, into fragmented, disordered energy that's sprinkled around among the particles. You okay with the idea of there being thermal energy? It's, I'm sort of pulling it out of a hat, just saying, here it is. It is not a completely different type of energy. It is little bits of kinetic and potential energy. It's all sprinkled around among the atoms and molecules. And because of its division and its sort of statistical distribution among all the particles, it's hard to do anything with it. You've lost track of all the little bits. And I did this on the lecture video, it's just like if you smash some beautifully organized thing. You take a glass sculpture and you just smash on the floor. The glass is all still there. The energy's all there. Everything's still there that was there before. And what won't happen if you pick up the glass shards and smash and hit them again is they will not reassemble into the sculpture. Not because the laws of motion say that's not possible. The laws of motion are indifferent. And we'll say, yeah, sure, it can happen. All the shards, they could hit just right, and they'd stick together, and all the chemical bonds would remake, and everything would be great. The energy would go back into its original place, and woof, you'd have it right back the way it was. The laws of motion allow that. What doesn't allow that is statistics. The odds of that happening are fantastically small, so it never happens. It's one of those things that the odds are so incredibly, incredibly against that kind of thing happening that we can say with absolute certainty it will never happen. Just like it will never happen that you will win the lottery 1 trillion times in a row. 2 times in a row would already be really pushing it. 1 trillion times in a row, not going to happen. So thermal energy is shattered energy, broken up into little bits, and it's very hard to reassemble those in a way that will do work, for example. So getting back to the issue, this particular issue, just to show you, static friction doesn't waste energy. I'm using this just so I can move it. Static friction allows me, for example, to do energy on the bottle. I could use support forces for this, and I would be lifting it, doing work on it, lowering it, doing negative work, all very simple. So far, so good? If instead of going from the bottom and pushing up on it like that with a support force, I can grip it on the sides with my fingers. And now I'm supporting it not with a support force, because support forces on vertical surfaces are horizontal. I'm supporting it with frictional forces. Is that okay? And they happen to be static frictional forces because my fingers aren't skidding over the surface. And so if I now lift, I do work on the bottle with the help of static friction. I lower, I do negative work on the bottle with the help of static friction. But the accounting works out beautifully. Like the work I do on the bottle is exactly equal to the negative work the bottle does on me. The energy moves from me to the bottle. It stays in this beautifully organized form that can still do work and be useful. It's not thermal. All right? If, on the other hand, I skid my fingers up, ideally I would let them skid, as I would move my fingers up, skidding. I can't pull it off. I'll cheat. I'll hold it up here. Right? Skid, uh-oh. When I did that, I was maybe supporting it, but with sliding frictional force. And then if you start doing the accounting, how much work it did on me and how much work I did on it, it won't sum to zero. It'll end up negative. Some energy will have disappeared in that skidding process. And that will become thermal energy. So sliding friction always wastes energy somewhere as thermal energy. Static friction never does. Okay? Fun and games. I mean, you can just simulate this yourself with your hands. You grip your hands, no skidding, no thermal energy. You don't feel any increase in heat. But if you start scuffing your hands across each other, it gets hot, right? You must have done this. The extreme case, this is always an iffy one. Some years this works great, some years, eh. So this is the fire starter with a bow and a stick of wood. So there's a stick of wood pinched between two plates. And as I spin that stick of wood, it will slide in its sockets. And usually I can get some smoke out of this. Here we go. I'm certainly doing work on the bow. I'm pushing it. It's moving in the direction I push. I'm sorry about the noise. For an encore, I'll go after the chalkboard with a piece of chalk. All right, there we go. Smoke. Woo! Ha ha. All right. So there I was clearly starting with work, pushing it, moving in the direction I push. I was putting in the work, and it was coming out as thermal energy. Start the wood on fire. All right? What else? Anything else I want to show here? I think that'll do it. Okay, so that brings me really to talk about wheels themselves. Let me get rid of this guy again. Don't need that. This guy, if I try to drive it around, it's going to be experiencing lots of sliding friction. The simplest alternative is to put rollers underneath it. And now those rollers, as the wagon moves, there is no sliding going on, assuming I do it right. It's hard to get it to work really nicely. But if you think about what the rollers are doing, they are touching the surface of the ground, for example. As they roll, they touch the surface of the ground, and they lift off, kind of like a wheel does. And this sort of leads into a wheel. The wheel, as it moves to the right, doesn't skid. Its surface does touch the table, but it's always landing and leaving. Touch and release. Okay? It never slides across. If I did sliding, first we'd make thermal energy, we'd wear out the wheel, we'd wear out the table. That's not what I want. Let it roll. So when things roll, the surfaces come together, and then they separate. They never scoot across each other. And that's the beauty of a roller or a wheel. A roller has many problems, one of which is you have to keep getting the roller. The rollers only go half the speed of the vehicle. So they go at the average speed between the two surfaces. And since you're driving on pavement, the pavement's not moving, the average speed of the roller is halfway between the vehicle speed and nothing. So you have to keep going out, picking up the roller from the back and putting it in front of it, right? So this works great if you're in one of those old societies where they had people who would work for you for nothing. Not a good situation anymore. Not acceptable. So you can't do that anymore. So we need wheels that come with us for free. And wheels do this. Wheels have this lovely property of, if I push this wheel to the right, it will not skid on the surface the way a wagon would. Instead, the wheel will begin to roll. And it will touch and release, touch and release. It will experience only static frictional forces. And that's, just to summarize, it's experiencing no sliding friction anywhere. And it's really introducing almost no forces along the direction of the wheel's roll. The wheel rolls essentially for free. I mean, I can get it started, of course, and it'll go across the whole room, which is itself kind of interesting until it hits something. Well, we'll come to the fact that why doesn't the wheel fall over? The single wheel actually steers itself, amazingly enough, so that it tends not to fall over. We will come back to that because that's the same principle that allows you to ride a bicycle no hands. You know, why don't you fall over when you're riding no hands? It's because the bicycle steers itself naturally. And that's part of the process right there. Anyhow, the point of this is not to get off on that tangent, but to notice that the wheel was just coasting beautifully. It was experiencing, once it got started and everything, it was experiencing no force forward or backward, to your right, to your left. It could, however, experience forces across its motion. Those would be static frictional forces. Whenever the wheel lands, like this, it's going to continue rolling to the right. But if something were to come along and try to push it away from you, it fights by way of static friction. The bottom of the wheel and the top of the table are actually gripping each other, and they don't like to skid. So they won't go left or right. So that allows you to do things like steer. It gives you the forces you need to direct the vehicle. When you don't want to go dead straight. Straight's easy because that's inertia. But if you want to do something different, you want frictional forces to help push. And so you can get static frictional forces. And so a wheeled vehicle, long and short of it, is a wheeled vehicle gets rid of sliding friction for all practical purposes. I mean, maybe there's a little bit around. And it uses static friction to do interesting things like get you started moving, or stop you, or turn the vehicle. Those are all done by way of static frictional forces between the bottom of the wheel that's temporarily touching the ground and not skidding, and the ground. They push on each other, and you can guide the vehicle. So you don't want to get rid of all of friction. You want to get rid of sliding friction. Is that okay? I will ask you one question here, and then talked in the. Do I want to do it? Yes. Okay. In the lecture video about the two types of wheels, free wheels that turn when the vehicle heads forward because they are loose. They're not attached to anything, they just turn. This wagon has purely free wheels. There's no engine to turn wheels, so the wheels turn only because you move the wagon. The other kind of wheel is called a powered wheel, which is turned not by the ground but by way of friction, but by an engine. The engine turns the wheel, and those wheels are used to propel a car forward. So what I want to do is ask you for a free wheel. So when you pull a wheeled cart, like my wagon, and it's accelerating forward, why do the wheels turn? Basically, this is asking, why do the wheels turn? Just to make sure you think about this. There's no engine turning the wheels. They're just. You okay with the question? Think you can find the answer? Go look for the answer. This time, I'm glad to see the majority of you are getting the right answer here. All right, I'm going to give you another 10 seconds and then call it. All right, ready, stop. And the correct answer is C. The wheel experiences a static frictional force that points backward. And I could do it with a wagon, but let me just do it with a bigger object, like this big wheel. So we're part of a big wagon that's going to head to the right. And suppose there were no friction. We grease everything, which incidentally sort of kills off both kinds of friction by introducing a liquid layer that doesn't care and basically doesn't exert frictional forces. Suppose we do that, we lubricate it. In that case, the wheel would, as the vehicle moved forward, the wheel would move forward. And the bottom of the wheel would be moving to the right relative to the table. So that's the danger of not having friction. However, there is friction, and friction doesn't like the bottom of the wheel moving to the right on top of a stationary table. So the table and the bottom of the wheel will push on each other, trying to maintain the same velocity. And the table's going to win. So the table's going to try to keep the bottom of the wheel motionless. And to do that, it has to push the wheel to the left, because the wheel's going to start moving to the right. So it pushes the bottom of the wheel to the left. The backward force of static friction, it's between two surfaces that are not sliding. It pushes to the left and causes the wheel to roll. That force, exerted as it is, at the bottom of the wheel has a lever arm to work with. Lever arm down, force toward me, that's a torque. And it's a torque away from us. And it causes the wheel to spin. It gives the wheel undergoes angular acceleration, the whole works. All right? So hopefully that's followable, and you can see the right answer there is C. Free wheels turn because friction forces them to do that, torques them, twists them, makes them go. Powered wheels do the reverse because they're spun not by the ground, but by an engine in the ground actually tries to stop them from spinning. And in doing that, it pushes on the whole vehicle and propels the vehicle forward. Any other questions about wheels, static friction, sliding friction? There's a question just asking about work, positive and negative, just a reminder that when I push up on an object, which I'm doing, and it moves upward, I am adding energy to it by way of doing work. The force I exert on it is up. The distance it moves is in the direction of the force. I do positive work on it. I add energy to it. If I do the opposite, I push up on it as it moves down, because my force on it and its movement are in opposite directions, the accounting is a negative amount. I gave the bottle a negative amount of energy, which lowers its energy. And it's now back where it was, I sucked the energy out of it. The other way of looking at it is from the bottle's perspective, it did positive work on me on the way down. It gave me back the energy. All right? Yeah, Tori. Oh, how do I do positive work on me if I don't move? This is an interesting question because work is always, I've never found a proper language for this. It's a microscopic story. Don't look at me, look at my hand. It's not about me, it's about my hand. If my hand is pushing on the bottle, as the bottle moves up, my hand is doing positive work on the bottle. If as I lower it, the bottle is pushing down on my hand as my hand moves downward, it's doing positive work on my hand. So don't get lost in the bigger picture. Just a little picture. Look at who's exerting the force on whom and who's moving. And everything else, irrelevant. So, for example, if I were standing in an elevator and the elevator is going up to the 800th floor, very big building, and the question on the test is this guy doing work on the bottle? The answer would be yes. It doesn't matter that you could replace me with a statue, right? I would still be doing work on the bottle as it goes up because I would be supporting the bottle's weight as the bottle moved up. It doesn't matter, you know. The fact that I'm a statue and not able to do anything interesting other than just be there is irrelevant. Yes, the elevator is doing work on me, and I'm conveying some of that work to the bottle. if I lift the bottle myself, of course, the energy never came into me by, nothing pushed on me to give me energy. I had it to start with. And I'm transferring some of my energy to the bottle. The statue transfers some energy from somebody else to the bottle. All right? Yeah, David. When I grab the bottle from the side, to the extent that I'm just lifting up and down like this, it's all frictional forces. There are support forces here, but they're canceling. My thumb is getting a support force to the left, and my fingers are getting a support force right, and the forces, well, are back, and I'm exerting support forces on the bottle. They cancel. How do you know that? Because the bottle is not accelerating left or right. If I get rid of my thumb, of course, the bottle goes off, accelerates. So the support forces are all canceling, boring, and the frictional forces are now canceling the weight. Is that okay? So we use frictional forces all the time. And you know from experience, you can only get, support forces you can get as strong as you like, depending on your personal strength. Frictional forces have a limit, right? You get to a point where the frictional forces, static friction gives up. And you know that when you try to pick something up with particularly when your hands have something on them and stuff, you try to pick a really heavy thing up, it slips. You can't get enough static frictional force to maintain the grip. And you begin to drift over into the world of sliding friction. All right? So the more reliable force to use to pick something up is a support force. So instead of taking a dumbbell, you can pick it up like this, that's friction, and it slips through your fingers. But if you go under it and push up, now it's a support force. That's sort of limitless. All right. Other questions? There's one more here, or at least. When a car locks its brakes, but still turns, are sliding forces making it turn? So we slam on the brakes. Actually, this is a really interesting question. When you slam on the brakes, or you hit them, let's not slam them completely, but push really hard because you want to stop quickly. If you pick things carefully, you will, the wheel will still land and leave. You will not exceed, the wheel will begin to exert static frictional forces on the pavement, and the pavement will exert static frictional forces on the wheel. They will be pushing on each other as they try to start skidding. As long as you don't stop too fast, too hard, the wheel will continue to roll, despite the fact that there are these big static frictional forces from one on the other. The wheel will continue to roll. You will continue to be able to steer the vehicle, and there won't be any wear and tear on the tires or thermal energy created by the tires. Where energy will be coming out of the vehicle, where will it be going? Into the brake system. The brake system is designed to turn energy into thermal energy in the brakes. They do get very hot, and part of the design of brakes is, at least this is in older vehicles, non-hybrid or electrics, it's turned into thermal energy, wasted. And sometimes it can destroy the You've seen truck runaway ramps. Why do they have those? Because it is possible in a truck, which has so much kinetic energy when it's moving, because it's got so much mass, it can burn up its brakes. And if that happens, it loses its brakes. What do? Well, you've got to stop the vehicle. How do you do that? Put it on a runaway ramp. Okay? The point of this discussion, though, still is that when you step on the brakes carefully, trying to stop as fast as you can realistically, you don't skid the wheels. The wheels are still gripping the surface by way of static friction and going. If you stomp too hard on the brakes, you can lock the wheels. So they stop turning absolutely completely. And now you are riding not on a rolling device, but on a rubber bumper that happens to be wheel-shaped. It skids. You have no control of which way the vehicle is going to go. It's going to go inertially. Its direction of travel will be determined entirely by inertia, not by your steering. Pick any direction you like, it's the same. Okay? And you will get wear and tear at the surface, so you're going to leave a burned rubber streak on the road and wear out your tires. And the other thing is, the force of sliding friction is weaker than the force of static friction at its best. So you won't stop as fast, in all likelihood. So this is why you don't actually want to freeze the wheel. You want to let it continue to roll, but make it experience big stopping static frictional forces with the pavement. And modern cars have anti-lock brakes for this very reason. There's sophisticated devices that watch the rotation of the wheel and try not to let the wheel stop turning. They want the wheel to continue turning and keep gripping the pavement, give you steering, give you a faster stop than if they lock. And you've probably seen you got a car, they'll tell you, oh, we're in traction control mode, we're trying to keep your wheels from skidding. You've either seen that or you felt it. On ice, it's particularly noticeable. You slam on the brakes on ice, and your wheel tends to lock very easily and starts skidding, and the car goes, oh, this is bad, and tries to fix it. And you can feel the machinery in the car trying to get your wheel rolling again. Is that okay? When you do lose the traction, as I pointed out, and you're now not on wheels anymore, you're sort of on rubber bumpers, just with no directional control, you go inertially. This is why in the winter, when you lose traction, for whatever reason, you tend to go as inertia had in mind, straight, at constant speed, constant velocity. And that means that cars, when you hope none of this ever happens to any of you or people you care about or anybody actually, but if you go looking for where do they go off the road on a slippery stretch? They go off the road on the outside of a turn. Why? Because as the turn goes, they go inertial, which is straight, and that's the outside of the turn. So that's the tendency. All right. So can a statue do work on a bottle? Absolutely. So here I am, I'm a statue, I'm riding an elevator, I'm going up, and some Mike Myers thing. So during that time, the issue is, did the statue do work on the bottle? Absolutely. The statue was pushing up on the bottle, and the bottle moved up. End of story. So what you might quibble about is like, well, so where did that energy come from? In a human, it might well have come from breakfast. In a statue, it didn't come from breakfast. It had to come into the statue through the statue's feet. The elevator did work on the statue's feet, which did work on the torso, which did work on the arm, which did work on the hand, which did work on the bottle. Okay? So you can watch the energy flow through. All right, that said, now let me shift over and talk about bumper cars. And I don't need this for the second. I can probably do this without any. Did go away. Okay. Bumper cars. When bumper cars are hitting each other, which is all the point of bumper cars is to smash them into each other. They are transferring conserved quantities. I mean, one way to look at it is they're transferring conserved quantities, and we've seen one conserved quantity so far outside of the lecture videos, and that is energy. Energy. It's the meaning of it being conserved is that you can't create it or destroy it. You can only move it around. It happens that you can hide energy in the form of potential energies. But the total amount never changes within an isolated system. So it just moves from one to the other, changes forms, and so on. It is what's known as a scalar quantity, meaning it has no direction aspect to it. It's just an amount. And it's measured in joules, which is a shorthand name for a Newton meter, the unit of the SI or metric unit of energy. All right, so we watch energy moving around. But there are two really interesting conserved quantities that show up all the time in everyday life, but certainly in bumper cars. The first of these is known as momentum. And so a word you've heard your whole life, but for physics, what momentum is it is a conserved quantity in nature. And you can't create it or destroy it. It is a vector quantity. It has a direction. The direction matters a lot. So right now I've got no momentum, and I'll get me some, okay? So I got some momentum. I actually got it out of the ground with the ground's help. I now have momentum to the left. I'm carrying it with me, and I give it to the wall. That does, not very convincing like that, but let me do it with a cart, because if I'm walking along, I can cheat all over the place. These carts tend not to go very straight. I'm threading the needle here, so we'll give it a try. So right now I've got no momentum. Remember, momentum has a direction, so I've got 0 momentum, 0, no direction of any interest. And I'm going to get some momentum to the right. How am I going to get that momentum? I'm going to get the wall to give it to me. I'm going to give the wall leftward momentum, which you won't notice because the wall is so massive, the consequences of giving it some leftward momentum are negligible. But it's going to respond by giving me an equal amount of rightward momentum. That will leave momentum conserved. No, we're not going to create any or destroy anything. I'm just going to give it some left. It's going to give me some right. Grand total, nothing. Once I've got it, I got it. Okay, so here it comes. Ready? All right, I've got it. And in principle, I can't stop. I got to keep going because I'm carrying the momentum with me. And to stop, I have to give it to something. So I'm going to give my rightward momentum to the wall, and that undid the leftward that I gave over there. We're all back to sort of everything, back to normal. But during that time, I was truly carrying this conserved quantity called momentum. I was also carrying some energy, but that's another story. So let me get some leftward momentum out of the wall. I'll give it rightward momentum. It'll give me leftward. I got it. I can't stop, can't stop. Got to keep moving. Whoa, I threaded the needle there. All right, now I'm going to give it to the floor, to the step. But during that transition, during the transit, I was carrying that stuff. Is that okay? Yeah. Wes?
So what I'm wondering is when you give that momentum to the wall,
yeah.
where does that energy go from the wall?
Okay. First off, energy and momentum are different. Just for point of, so don't be careful using them interchangeably. They are two independent conserved quantities. But the question, Wes's question is when I gave momentum, presumably to the wall, I said, I gave it a good shove. Yes. So what happened to it? Because nothing seems to happen. The momentum that something carries, it turns out, is a very simple calculation. It's the mass of the object times the velocity of the object. That's all it is. And velocity, being a vector quantity having a direction, gives a direction to momentum. So if I've got velocity to the right, I have momentum to the right. And my momentum is just my mass times my velocity. That's all it is. Is that okay? So when I pushed on the wall, let's say it gave me 100 units of momentum to the right. I gave it 100 units of momentum to the left. I have to move fairly fast to carry 100 units of rightward momentum because I don't have very much mass. So the product of a little mass times it has to be a big velocity to have that much momentum. The wall effectively is the whole Earth. And therefore, the mass is unbelievably huge. Therefore, it's able to carry that momentum with the most infinitesimal velocity that you never notice. But it actually does affect the wall. So you're all probably just like me as a kid, right? You say, Dad, when I do this, am I really shaking the whole Earth? You naturally asked this question, didn't you? And the answer is yes, absolutely. So when I do this, when I push on the ground, it gives me upward momentum. It loses the upward momentum by way of gravitational pull. It reels me back in and sucks the upward momentum out of me. But during that jump, I gave it downward momentum, it gave me upward momentum. You could see the upward momentum in me. You couldn't see the downward momentum in it because it's too big and massive, but it's there. And when you know this also, from the floors aren't perfectly rigid and stuff, so it's not like I really pushed on the whole Earth initially. I pushed on a piece of the Earth. And this floor is pretty stiff, but the floor, you've been in houses and stuff like that where you do this and the whole floor jiggles around because you gave it downward momentum and it moved. All right? So the transfer of momentum it's truly conserved. You give some momentum to something, I don't care how big it is, it actually got that momentum. And that will have affected it. Maybe not enough for you to notice, but there's instruments that can notice it. All right? The act of transferring momentum is known as doing an impulse. It's an awkward language, to do an impulse on something. The way you transfer momentum is by pushing on it for time. You know how to transfer energy, you did work. You push on it for a distance. That's not what you need to do to transfer momentum. You need to push on it for time. And so the harder you push on something and the longer you push on it, the more momentum you transfer. All right? It doesn't matter whether it moves or not. That's irrelevant. And if it doesn't move, for example, if I push on this table, I am truly transferring rightward momentum to the table. Nothing much is happening. Why? Well, in part because the table's so massive. But nothing's happening to me either. It's because I'm transferring rightward momentum to the table with my hands. The table, in turn, is transferring rightward momentum to the ground. And the ground, in turn, is transferring rightward momentum to my feet and undoing. It's going around in circles and getting nowhere. The table's giving me leftward momentum. I'm bleeding that leftward momentum out through my feet. I'm accumulating none. Put me on wheels, I'll accumulate it. Okay? Trying to show you some of these things. This bumper car story. So this is a linear bumper car track. It's classic physics demonstration equipment that I haven't used for years. But there's a bumper car sitting there. If this is all set up perfectly, it would just sit there. It's got air in it to try to get rid of the friction. But if I take a bumper car and smack it into the other one, this one gave all of its momentum. They're playing exchange the momentum. This is momentum to the left being transferred to that one, which is carrying it. It goes off the wall and ends up with momentum to the right, having pushed hard on the wall. They're bouncing back and forth. It's a little more complicated than I like to make the story. But the basic idea is the collision between the two at the center. You can actually one cart can convey to the other cart all of its momentum. And the first cart stops and the second cart starts. And you've seen toys that do this. The hanging balls on strings that you bring one in and it smacks the whole row, and the last one of the balls pops out. You can do this with coins, a row of pennies. You smack one penny in, the whole row seems to do nothing except the last penny jumps out. That's momentum working its way through them all. So that's momentum. What I want to finish up, I'll show you more about the transfers of momentum on Friday. I want to show you the other conserved quantity before we finish completely. I got 2 or 3 minutes left. The other conserved quantity is the conserved quantity. So momentum is the conserved quantity of going somewhere, of moving, of translating. There's a conserved quantity of rotating also, known as angular momentum. It is independently conserved, unrelated to momentum, unrelated to energy. And it shows up as things rotating. So the same idea as with me flying across the room, carrying momentum, unable to stop while I've got the momentum, same thing happens with rotation. Right now I've got no angular momentum. Angular momentum turns out to be the product of my rotational mass times my angular velocity. And my angular velocity is 0, so I've got no angular momentum. If I get some, though, from the ground, which I'll do with it by way of twisting, I'll twist the ground one way, giving it angular momentum one way, and it will give me angular momentum the other way. I'm going to give it downward angular momentum, and it's going to give me upward angular momentum. Ready? Gets that? There, I've got it. Okay? It's upward because the right-hand rule. My thumb's up here, right? This is the way I'm turning. So I've got it. I can't get rid of it until I give it to the ground again, so I'll give it to the ground. And the fun and games version of this, so I might as well do this because I can. I'm going to play, with those two carts, we're trading off momentum one to the other. We can do that live with 2 people on carts, too. I'm going to trade off momentum back and forth with this wheel, angular momentum, with this wheel. So I'm going to get the wheel spinning, chock full of angular momentum. The angular momentum right now is away from you, but I can rotate this. It's a little of a complicated story. Woo, ramming speed. Whoa, it's a little out of round today. I don't know why that's the case. Right now it's turning up. So it's got upward angular momentum, I have none. If I flip it over, it's going to have downward angular momentum, and I have the missing upward angular momentum. I'm rotating like this. And if I flip it back down, we're back to where we started. This wheel needs service. But this demonstration is one that ideally you would try yourself because the act of turning it over is hard work. It's twisting me like crazy when I do that. And the point is that we're exchanging this conserved quantity known as angular momentum. It's hard to follow my story. I'll do it again properly on Friday.